GJ 486b is a rocky world with stronger gravity than Earth. GJ 486b is about 30% larger than the Earth and 3 times as massive. It orbits a red dwarf star in just under 1.5 Earth days. It is too close to its star to be within the habitable zone, with a surface temperature of about 800 degrees Fahrenheit. And yet, Webb observations show hints of water vapor. The water vapor could be from an atmosphere enveloping the planet, in which case it would need to be continually replenished due to losses from stellar irradiation. But an equally likely possibility is that the water vapor is actually from the outer layer of the planet's cool host star. Additional Webb observations will help answer the question: can a rocky planet maintain, or re-establish, an atmosphere in the harsh environment near a red dwarf star? The most common stars in the universe are red dwarf stars, which means that rocky exoplanets are most likely to be found orbiting such a star. Red dwarf stars are cool, so a planet has to hug it in a tight orbit to stay warm enough to potentially host liquid water, meaning it lies in the habitable zone. Such stars are also active, particularly when they are young, releasing ultraviolet and X-ray radiation that could destroy planetary atmospheres. As a result, one important open question in astronomy is whether a rocky planet could maintain, or re-establish, an atmosphere in such a harsh environment. To help answer that question, astronomers used NASA's James Webb Space Telescope to study a rocky exoplanet known as GJ 486b. It is too close to its star to be within the habitable zone, with a surface temperature of about 800 degrees Fahrenheit, 430 degrees Celsius. And yet, their observations using Webb's Near-Infrared Spectrograph (NIR spec) show hints of water vapor. If the water vapor is associated with the planet, that would indicate that it has an atmosphere despite its scorching temperature and close proximity to its star. Water vapor has been seen on gaseous exoplanets before, but to date no atmosphere has been definitively detected around a rocky exoplanet. However, the scientists cautions that the water vapor could be on the star itself, specifically, in cool star spots, and not from the planet at all. GJ 486b is about 30% larger than the Earth and 3 times as massive, which means it is a rocky world with stronger gravity than Earth. It is expected to be tidally locked, with a permanent day side and a permanent night side. GJ 486b transits its star, crossing in front of the star from our point of view. If it has an atmosphere, then when it transits, starlight would filter through those gases, imprinting fingerprints in the light that allow astronomers to decode its composition through a technique called transmission spectroscopy. The team observed 2 transits, each lasting about an hour. They then used 3 different methods to analyze the resulting data. The results from all 3 are consistent in that they show a mostly flat spectrum with an intriguing rise at the shortest infrared wavelengths. The team ran computer models considering a number of different molecules, and concluded that the most likely source of the signal was water vapor. While the water vapor could potentially indicate the presence of an atmosphere on GJ 486b, an equally plausible explanation is water vapor from the star. Surprisingly, even in our own Sun, water vapor can sometimes exist in sunspots because these spots are very cool compared to the surrounding surface of the star. GJ 486b's host star is much cooler than the Sun, so even more water vapor would concentrate within its star spots. As a result, it could create a signal that mimics a planetary atmosphere. A water vapor atmosphere would be expected to gradually erode due to stellar heating and irradiation. As a result, if an atmosphere is present, it would likely have to be constantly replenished by volcanoes ejecting steam from the planet's interior. If the water is indeed in the planet's atmosphere, additional observations are needed to narrow down how much water is present. Future Webb observations may shed more light on this system. If the planet has no atmosphere, or only a thin atmosphere, then the hottest part of the day side is expected to be directly under the star. However, if the hottest point is shifted, that would indicate an atmosphere that can circulate heat. Ultimately, observations at shorter infrared wavelengths by another Webb instrument, the Near-Infrared Imager and Slitless Spectrograph (NIRISS), will be needed to differentiate between the planetary atmosphere and starspot scenarios.